This video is for lesson 4 of the GCSE motion topic entitled Velocity Time Graphs. By the end of the lesson you should be able to interpret a velocity time graph. Recall that the steeper the slope, the greater the acceleration. Be able to use the gradient of VT graph to calculate acceleration, and if you are doing the higher paper, use the area underneath the graph to calculate the distance travelled. Okay, before we get going, a quick starter based on last lesson's work. A ball is dropped from a very tall building, is accelerated by the force of gravity at a rate of 10 meters per second squared. I'd like you to tell me what the speed is after 1 second, 2 seconds and 10 seconds. And then finally, those speeds which you thought about aren't actually attained. Why do you think that those speeds might not actually be attained in real life? So pause the video, have a think, we'll go through the answers in a moment. Okay, so this little question is testing you on what you understand by the acceleration being 10 meters per second squared. It means that for every second of its flight it increases its speed by 10 meters per second. So if it's dropped, its initial speed is 0. If it's in flight for 1 second, then its speed after 1 second will be 10 meters per second. If it's been allowed to fall for 2 seconds, then its speed will increase to 20 meters per second, an increase of 10. If it's been falling by 10 seconds, then its final speed should be 100 meters per second. Now I say should be, as you'll be aware from your early work on forces, as things fall through air, they experience a force of air resistance, and this acts to reduce the resultant force downwards. So you actually have a smaller force downwards, and therefore you'll have a smaller acceleration. So these figures, particularly the higher ones here, will actually be a little bit less than the predicted values due to air resistance. A couple of lessons ago we looked at distance or displacement time graphs. Today we're going to look at velocity time graphs, and the big difference to note is the axis here. It's labelled with speed or velocity. Whilst the shapes of these graphs may look very similar to distance time graphs, they mean very different things. Now unfortunately I can't pause this video as it goes through, this animation as it goes through, so I'll have to talk over it. So you might want to replay it just to get the gist of it. Okay, so if we started off, first off, time 0, its speed is 0, so it starts from scratch, from stationary. And as time goes by, it increases its speed, it accelerates. Now because it's a straight line, we get constant acceleration. A horizontal line this time means a constant speed, not 0. And again, it accelerates in a uniform manner, and then its speed remains constant again. So just to recap, a straight diagonal line means constant acceleration, it's increasing its speed at a steady rate. A horizontal line means it's travelling at a constant speed, it's not standing still, a constant speed. And then this second line here isn't as steep as the initial one, sorry, steeper than the first one I should say, and so the acceleration is greater. Now you have to be able to perform calculations from velocity time graphs just like you did with distance time graphs. So let's see how we do that then. If you're asked to calculate the acceleration over the first 20 seconds, then you're going to use the formula change in speed or change in velocity divided by time taken. So here the change in velocity is 20, the time is 20, so the acceleration is 1 meter per second squared. So for every second of its journey, it's increasing its speed by 1 meter per second. We did say here that the line is steeper, so we're expecting a greater acceleration. And again, we're going to use acceleration equals change in speed divided by time. Now notice the change in speed isn't 60 because you're already starting at a speed of 20 here. So you're going from 20 to 60, which is a change of 40, and it's taking you 10 seconds to do that. So we put our numbers in, and we end up with an acceleration of 4 meters per second squared. These two sections here, we said that the speed or velocity was constant, didn't change, so the acceleration is 0. So 0 meters per second squared and 0 meters per second squared. Okay. The only other thing to be aware of from a velocity or speed time graph is that you can actually work out how far something has travelled by calculating the area underneath the graph. If you look where my cursor is here, can you see that we've got a triangle there? So we could work out the area of that triangle, half the base times the height, plus an area of a rectangle, go right the way along here, then we'd have a triangle here and another rectangle here. Use the dimensions on the graph to work out the area underneath the graph. Now I'll be going through that in a problem to show you how to do that, but just be aware of that. The distance travelled is the area underneath the graph. Okay, so can you put the title velocity time graph? This needs to go into your notes. So you just strictly speaking need the writing here. Insert the coloured clouds into the grey clouds. You can do a little sketch by the side if you wish, but can you pause the video and do that now? Okay, and your answers. Velocity includes the speed of an object and the direction in which it travels. Velocity time graphs can be used to see when an object is moved with constant velocity or acceleration. This is for your notes. Can you put the title velocity time graph problem? Can you pause the video and answer the first 4 questions? Question 5 we'll work through together. Okay, so pause it, answer questions 1 to 4. Okay, answers then. 0 to 10 seconds, diagonal straight line, so we have constant acceleration. 10 to 20, we have constant velocity, horizontal line. 20 to 30, we have a lower constant acceleration, the gradient isn't as steep. And the reverse here shows that the object is decreasing its speed, so it's deceleration, so it's a constant deceleration. Number 2, how far has the object gone after 10 seconds? Nice and easy, this we just read off the graph. This often catches people out on how easy that is. So after 10 seconds it's travelling at 40 meters per second. Acceleration from 20 to 30. Okay, so it's going from 40 meters per second to 60. So the change in speed is 20. It's taken 10 seconds to do it. 20 divided by 10 gives us 2 meters per second squared. And number 4, the deceleration, same idea. Acceleration is change in speed divided by time. This time the change is going from 60 to 0. So the change is minus 60. And that minus 60 is important, the minus sign there. It's taken 20 seconds to do it. So the acceleration is minus 3 meters per second squared, which if you remember is a deceleration. To work out how far the object has travelled altogether, we need to work out the area underneath the graph. So we need to split it into regular shapes that we can find the area of. So the first one is this little triangle here. So that little triangle has an area of half the base, 5, times the height, 40. So 5 times 40 will give you 200 meters. The next shape I'm going to use is this rectangle here, which is 30 minus 10, 20, 40 up, 800 meters. The next shape is this little triangle here. So from there to there is 10, half the base is 5, times the height is 20, so we get 100 meters. And then we got this last little triangle here where it's decelerating. So half the base times the height gives us 600 meters. Now if you add all those together, you get an answer of 1700 meters. So break the graph down into regular shapes whose area you can determine using the scales on the side here, and then add them all together. Please make sure that you've got a copy of that in your notes. Also for your notes, I'm sorry I don't have time to talk through this, non-uniform acceleration simply means when you don't have straight line velocity time graphs. Pause the video and make a copy of the slide there. Could you now attempt the questions listed above?